Hey, my friend. Tonight we're exploring a quantum idea that sounds impossible, using the future to make sense of the past. I'll explain it slowly and clearly, no stress, just gentle science, so you can learn a little and fall asleep a lot. Chapter 1. Can the future change the past? It is one of the strangest sentences people attach to quantum physics, and it is also one of the easiest to misunderstand. The future changes the past can sound like time travel, like rewritten diaries, like history being edited after the fact. Quantum mechanics does not do that, not in the way stories do. Yet there are real experiments where a later choice changes what kind of past you are allowed to describe, and that can feel uncomfortably close to the idea of a backward influence. The key is learning to separate two things that our everyday intuition blends together: what happened in the world and what we can correctly say happened, given the information the world ends up recording. In ordinary life, the past feels solid because it is constantly being copied. Light bounces off a cup and into countless directions. Some of it reaches your eyes, some reaches a camera, some warms the air and the wall. Sounds travel, footprints remain, and tiny vibrations ripple through objects. The environment does not keep secrets. Every interaction leaves traces, and those traces become evidence. Once evidence exists in many places, it becomes effectively impossible to undo. This is why the classical past feels like a single track. Events leave durable records, and durable records lock the story in place. Quantum physics begins in the opposite situation. A quantum system that is sufficiently isolated does not necessarily create durable records about its own path through the world. Instead of carrying a single hidden history like a tiny billiard ball, it is described by a quantum state that predicts probabilities for different outcomes. This is not just a statement that we do not know the answer yet. It is a rulebook for which answers can exist together and how alternative possibilities can combine. In quantum theory, possibilities can interfere. That word matters because interference is the mechanism by which the world refuses to behave like a collection of tiny classical objects with clear, independent trajectories. The simplest place to feel the weirdness is in interference experiments. If a quantum object can reach a detector by two alternative routes, and the experiment is arranged so that those routes are indistinguishable, the detection probability can show an interference pattern. That pattern is not what you would expect if the object always secretly took one route or the other, and you were merely ignorant of which. The pattern behaves as though the alternatives remained coherent, meaning the quantum description treated both alternatives as part of one combined process. But if you add a device that records which route was taken, or even if the setup makes that information available in principle, the interference fades, the probabilities change. The world begins to look classical again. So far, this sounds like a simple rule. If you learn the path, you lose interference. The delayed choice idea is what pushes it into the territory of the future changes the past. In delayed choice experiments, the decision to preserve indistinguishability or to reveal which route information is made only after the quantum object has already passed the region where, in a classical picture, it would have chosen a route. The apparatus is arranged so that the choice of what kind of measurement to perform comes late. Sometimes it is made so late that, if you insisted on the classical story, you would have to say the object must have already committed to a path before you decided what sort of question you would ask about it. And yet, the results agree with standard quantum predictions. If you perform the measurement that preserves indistinguishability, you see interference. If you perform the measurement that extracts which route information, you see a pattern consistent with distinguishable alternatives. The late choice determines which pattern you observe. This is the moment where many people feel the floor shift. How can an object behave as if it went through both routes when you choose to look for interference, but behave as if it went through one route when you choose to look for a path, especially if that choice is made after the object has already passed the point where the routes split? The tempting conclusion is that your later decision reached backward and changed what the object did earlier. Quantum mechanics suggests a different lesson. When no stable record exists, the question, which road did it take, is not the kind of question that has a measurement-independent answer. That is not a philosophical trick. It is a practical statement about what the theory allows you to assign consistently. If the experimental arrangement never creates a durable record of the route, then insisting that a definite route existed anyway is adding an extra claim that does not improve predictions and can create contradictions with the observed interference. In the quantum description, the route is not a hidden fact waiting to be uncovered. It becomes a fact only when the world contains an actual record that distinguishes the alternatives. This is where the idea of measurement becomes more than looking. In quantum physics, measurement is the physical process that turns delicate quantum information into a stable, classical record. A measurement is not just a human awareness. It is an interaction that correlates a system with a macroscopic device or with an environment in a way that can be copied and checked. When that correlation exists, it destroys coherence between alternatives that would otherwise interfere. That is why which route information and interference cannot both be fully present in the same run of the experiment. They correspond to different experimental conditions and different kinds of records. A quantum eraser experiment adds another layer that can feel even more like a backward influence. In such setups, which route information may be created indirectly, perhaps stored in a partner system or in an additional degree of freedom. If that information exists in principle, interference disappears in the basic detection statistics because the alternatives are distinguishable at the level of the total physical situation. But then a later measurement can be chosen that erases the route information, not by changing the past, but by measuring the partner system in a basis that no longer reveals which route. When the data are then sorted according to the later measurement outcomes, interference patterns can reappear within the corresponding subensembles. Again, the emotional trap is to say the later erasure changed what the object did earlier. But the total, unsorted detection counts do not suddenly transform. No late choice makes interference appear in the overall distribution. The interference appears only after you condition on the later outcome and group earlier events accordingly. This is the crucial point. The strange effect is not that the past has been rewritten, but that the correct description of the past depends on which information you include when you analyze the experiment. In a calmer light, this is a familiar idea wearing unfamiliar clothes. In ordinary statistics, learning new information later can change how you interpret earlier data. If you later discover that a certain background condition was present, earlier observations may become meaningful signals instead of noise. The observations did not change. Your inferences changed because the conditions you were conditioning on changed. Quantum physics takes this everyday logic and combines it with the fact that some questions, like which path, are not simply about ignorance. They are about whether a record exists that makes the alternatives distinguishable in the physical world. So, in what sense can the future predict the past? In a precise sense, it is about inference under two constraints: how the system was prepared and how it was later found. When you post-select on a particular final result, meaning you keep only the trials that end in a chosen outcome, you are describing a special subset of histories. Within that subset, quantum theory can assign probabilities for earlier hypothetical measurements that differ from the probabilities you would assign without knowing the final result. This can make it seem as though the later outcome is reaching backward. But what is really happening is conditional reasoning. You are not changing the earlier events. You are describing a filtered set of events whose statistics are different precisely because you filtered them. The most important protection against confusion is causality. If a later choice could controllably alter an earlier recorded outcome, you could send a message to the past. Quantum mechanics does not permit that. The backward-flavored effects appear in correlations that require later comparison of records, or in patterns that only emerge after sorting the data using information that is unavailable until the end. Nothing about these experiments allows an observer at the earlier time to detect, from their local data alone, what choice will be made later. The apparent retrocausality is not a usable signal. It is a feature of how joint probabilities and conditional subensembles behave in a theory that includes interference and measurement. This is why these experiments have such lasting scientific value. They force a careful separation between what is physically recorded and what is merely a story we would like to tell. Quantum theory is extremely disciplined about that separation. It says that if you want to claim the system took a definite route, you must have a physical record that distinguishes routes. If you arrange the experiment so that no such record exists, the theory warns you not to smuggle in a classical narrative anyway. You can still ask questions, but the answers must respect the structure of the measurements and the information they create. There is also a deeper theme, one that will matter later when we talk about two stories at once. Many of the fundamental rules used in quantum physics are compatible with time symmetry. Roughly speaking, if you reverse the direction of time while also reversing the relevant boundary conditions, the predictive structure remains consistent. Our lived experience, however, is not symmetric. We remember the past and not the future. Records accumulate rather than unaccumulate. That familiar arrow is closely tied to irreversibility, to the fact that evidence spreads into the environment and becomes effectively impossible to gather back into one place. The quantum experiments that feel backward are often the ones that carefully prevent evidence from becoming irreversible too early, so that the usual one-way storytelling has not yet been forced onto the system. When you put all of this together, a calmer conclusion emerges. Quantum mechanics does not say the future rewrites the past. It says that, at very small scales, the past is not always a single clean story of hidden facts waiting to be revealed. It is a structure of possibilities that becomes a definite story only when information is recorded in a way that cannot be undone. Your later measurement choice determines what information is recorded and therefore determines which kind of past description is consistent with the full set of records. Can your everyday world remain safe inside that? Your day has already left countless stable traces in your surroundings, in your routines, and in your memory. Nothing in these quantum puzzles can reach into ordinary life and disturb what you've already lived. You can let the question stay interesting, gentle, and contained, and allow your mind to loosen its grip on the day as you rest. Chapter 2. The one rule you need. Quantum outcomes are probabilities. If you keep only one idea from quantum physics, let it be this. The theory does not promise a single definite outcome for a single run of an experiment. It promises a set of chances. Given how you prepare a system and how you choose to measure it, quantum mechanics tells you how likely each outcome is. That might sound like a retreat from certainty, but it is a different kind of certainty. The probabilities are precise, stable, and testable. When the same preparation is repeated many times, the results form a distribution whose shape can be predicted in advance, even though the individual events remain unpredictable. In everyday life, probability usually enters because we do not know enough. You might say there is a chance of rain tomorrow because the atmosphere is complicated and your information is incomplete. Even the roll of a die looks random, mostly because you cannot control the exact starting conditions and the countless small influences during the roll. In a classical picture, if you knew all details with perfect precision, the outcome could, in principle, be predictable. Quantum probability behaves differently. In carefully controlled experiments, where the preparation can be repeated with extraordinary consistency, the outcomes still arrive as a distribution. You can reduce noise, isolate the system, cool the apparatus, and refine the technique, and the randomness does not vanish. What becomes clearer instead is that the randomness has a rule book. The distribution that emerges across many trials converges to the same predicted values again and again. Quantum mechanics is, in this sense, a theory of lawful statistics. A simple way to feel this is to imagine a measurement with only two possible results, like two different clicks from a detector. In classical thinking, the system carries the answer already, and the measurement reveals it. In quantum mechanics, a preparation can place the system in a condition where neither click is predetermined in the classical sense. The state is not a hidden answer you are failing to access. It is a complete predictive object within the theory. It tells you the probability of each click, and it tells you how those probabilities would change if you chose a different kind of measurement. This is why repetition matters so much. Quantum theory is not judged by whether it predicts a single event with certainty. It is judged by whether its probability predictions match the frequencies that emerge across many runs. When you send a large stream of identically prepared systems through the same measurement, the relative frequencies settle down. Over enough trials, the scatter shrinks and stable proportions appear. The agreement between those proportions and the quantum predictions is among the most repeatedly verified facts in modern physics. What makes these probabilities uniquely quantum is that they are not simply a reflection of ignorance about hidden classical details. In ordinary probability, it is often possible to imagine that there is a fully definite underlying situation, and you just do not know which one you have. The probabilities reflect uncertainty about a definite reality. Quantum mechanics can sometimes look like that, especially when the preparation is messy, but it also produces patterns that resist the hidden detail picture. The theory behaves as if the state is not a label for an unknown classical condition, but a different kind of object, one that encodes probabilities in a structured way that depends on the measurement you choose. A calm way to describe this without technical machinery is to treat the quantum state as a compact storage of predictive information. It is not a tiny classical object with a definite value for every question you could ask. Instead, it is a rule that connects preparations to measurement outcomes through probabilities. If you ask one question, you get one set of probabilities. If you ask a different question, you get another set. The crucial point is that these different sets are not independent guesses. They fit together consistently because they come from one state description. That is part of the discipline of quantum mechanics. It limits not only what you can predict, but also which probability assignments can be made without contradiction. This is also what people mean by superposition in its most grounded sense. Superposition does not need to be pictured as a particle being in two contradictory classical situations at once. It is better understood as the state carrying multiple possible outcome structures that remain coherent, meaning the relationship among possibilities matters, not only their separate weights. When coherence is present, probabilities are shaped by how possibilities combine. When coherence is lost, the probabilities behave more like ordinary alternatives that you would add in a classical way. This is not a poetic statement. It is a practical summary of why interference appears in some quantum experiments and disappears when the world contains information that distinguishes the alternatives. That distinction brings us to an important point for scientific clarity. Not all probability in quantum experiments has the same origin. Sometimes the randomness is genuinely quantum, meaning that even with an ideal preparation, the individual outcome is unpredictable. Other times, probability reflects ordinary uncertainty because the preparation is imperfect. If your source sometimes produces one state and sometimes another, then the overall statistics include a classical part that reflects which state happened to be produced on a given run. In modern language, the difference is often described as the difference between a clean, coherent state and a mixed situation that includes ordinary ignorance and environmental disturbance. Radioactive decay makes the irreducible part feel concrete. Consider a collection of identical, unstable nuclei. Each nucleus has a certain chance to decay within a given time interval. The collective behavior is highly predictable. You can describe how the number remaining typically decreases with time, and that behavior is stable across samples. But you cannot predict which particular nucleus will decay next. In the standard quantum description, there is no hidden clock you can read that schedules each decay moment in advance. What the theory gives you is the probability pattern, and that pattern is exactly what experiments confirm. Light provides another gentle example. If you send single photons toward a polarizing device, the photon is either transmitted or not, depending on how its polarization relates to the device's orientation. In some preparations, the result is certain. In others, it is probabilistic. You can repeat the same preparation and the same measurement and still get a random-looking sequence of individual outcomes, even though the long-run frequency locks into a stable value. This is not a statement about sloppy technique. It remains true even when the apparatus is engineered to be extremely stable. The uncertainty is not merely in the lab. It is in the structure of the quantum prediction itself. Spin measurements sharpen the point further because they do not map neatly onto an everyday classical picture. If you prepare a particle so that it gives a definite result when measured along one direction, and then you measure along a different direction, the outcomes become probabilistic. The probabilities depend on the relationship between the preparation and the measurement. But there is no need, and no consistent way across all possible measurements, to imagine that the particle carried a definite answer for every direction all along, with probability merely reflecting your ignorance. Quantum mechanics treats different measurement choices as different questions that cannot always have simultaneous, pre-existing definite answers in the classical sense. Now we can connect this rule back to the broader theme of this video without repeating the earlier chapter's focus. In quantum physics, probability describes what you should expect when a physical record is created. Before a record exists, many classical-sounding questions are not simply unanswered. They are not well posed in a measurement-independent way. What quantum mechanics gives you instead is a disciplined method for predicting the probabilities of future records under any chosen measurement. This is part of why later information can change what you are justified in concluding about earlier stages of a process. Your description is always tied to the records you actually have and to the measurement framework that created them. This is also where it is helpful to resist a common misunderstanding. Quantum probability does not require that a human mind creates reality by staring at it. The relevant ingredient is physical interaction that produces a stable record, something that can be copied, checked, and agreed upon. A detector does that. The environment can do that. In many modern experiments, the entire challenge is to prevent the environment from creating records too early, because premature record formation destroys coherence and changes the probability structure. The language of observation is convenient, but the physics is about correlations and records, not about consciousness. Seen this way, the one rule is not that reality is vague. It is that reality at small scales is lawful in a statistical way. Individual events are not predictable, but distributions are. The laws do not micromanage every detail, yet they still impose an exact structure on what patterns can appear. The same preparation interrogated in different ways yields different probability distributions, but those distributions are linked because they come from a single state description. And there is a quiet existential echo in that. If you let it land gently, the universe can be ordered without needing every moment to be pre-written. It can be coherent without demanding that every detail be controlled. In that sense, probability is not a lack of meaning. It is a softer kind of rule, and it leaves room for you to wonder, to accept uncertainty, and to keep moving without carrying the weight of perfect certainty. Chapter 3. What a measurement really does. In everyday language, a measurement sounds like a simple act. You look, you read a value, and you learn what was already there. In quantum physics, measurement is not merely a passive glance at a pre-written reality. It is an active physical process that changes what can be said about a system because it creates a record in the world. That record is not an abstract idea. It is a real, durable correlation between the system and something larger, a detector, an electronic circuit, a a photographic plate, a screen, a memory register, or ultimately the surrounding environment. When a measurement happens, something becomes fixed in a way that can be checked again later. The central question is not whether someone observed it in a human sense, but whether a stable imprint exists. To see why that matters, it helps to think about what a detector actually is. A detector is not a neutral window. It is an engineered amplifier. A tiny event, such as a photon being absorbed or an electron arriving, triggers a cascade. In a photomultiplier tube, one electron can knock loose more electrons, creating a measurable pulse. In a semiconductor sensor, a single absorbed photon can generate charge carriers that are collected and read as a signal. In a cloud chamber, a microscopic interaction seeds a visible track of droplets. In all these cases, the detector takes a small-scale quantum interaction and translates it into a macroscopic change. That macroscopic change is precisely what turns a fragile quantum possibility into a classical fact. Quantum theory describes the system before measurement in a way that assigns probabilities to possible outcomes. But the measurement device itself is also a physical system, and the key step is that the system and the device become correlated. If the system has multiple possible outcomes, the device becomes correlated with each of those possibilities. In a fully quantum description, the combined system is driven into a joint state where system outcome and pointer reading are linked. This is sometimes described as entanglement between the system and the measuring apparatus. The apparatus pointer, whether it is a needle position, a detector click, or a pixel value, becomes part of the quantum description during the interaction. If we stopped there, we would have a strange situation, a combined state that includes multiple potential pointer readings at once. But we do not experience pointers that way. We experience one outcome. A detector either clicks or it does not. A spot either appears at one location or another. This gap between the smooth quantum description of interaction and the single outcome we observe is the heart of the measurement problem, and it is exactly why measurement in quantum mechanics is treated with special care. One practical way quantum theory handles this is by distinguishing two kinds of evolution: a continuous, lawful evolution of the quantum state when the system is isolated, and a state update when a measurement outcome is registered. The update is not usually presented as a new force or a mysterious energy burst. It is presented as a change in what information you should use going forward, given that a particular record now exists. In other words, it is an update in the description conditioned on the recorded outcome. This can be understood in an operational way. Suppose you have a source that prepares a system in the same way each time. Before measurement, the best prediction you can make is a set of probabilities. When the measurement is performed, you obtain a particular outcome. And from that moment onward, you can make sharper predictions for future measurements, because you are no longer dealing with an unresolved set of possibilities. You are dealing with a specific branch of events that has left a record. The update rule is the theory's disciplined way of saying, now that the world contains this outcome, use the state that matches it for your next prediction. However, the deepest reason measurement feels one way is not the update rule itself. It is the physical irreversibility of record creation. Measurement outcomes are not delicate. They are amplified. They spread into many degrees of freedom. The detector heats slightly, an electrical pulse travels, a file is written, and the environment becomes correlated with the result. Once this happens, undoing the measurement would require gathering up an enormous number of scattered influences and reversing them with exquisite precision. In principle, quantum dynamics is reversible in many microscopic settings. In practice, measurement devices are designed to be irreversible because irreversibility is what makes a record reliable. This is where decoherence enters, not as a mystical explanation, but as a concrete physical mechanism. Decoherence is what happens when a quantum system becomes entangled with its environment in a way that effectively destroys the ability of different alternatives to interfere. The system's delicate phase relationships become inaccessible, smeared out into the environment. The result is that, for all practical purposes, the system begins to behave like a classical mixture of alternatives rather than a coherent combination. Importantly, decoherence does not require a human observer. It happens whenever a system interacts with many uncontrolled degrees of freedom, such as stray photons, air molecules, vibrations, or internal motions in a detector. In the context of measurement, decoherence explains why pointer states appear stable. A measuring device has certain macroscopic states that are robust, like clicked and not clicked, or one pixel being bright rather than another. The environment interacts differently with these macroscopic states, quickly scrambling any coherence between them. This makes interference between distinct macroscopic outcomes essentially impossible in ordinary conditions. Decoherence therefore explains why, after measurement, we do not see superpositions of different pointer readings. The world rapidly selects a set of stable, classical-looking outcomes, not by an extra postulate of consciousness, but by the relentless spread of information into the environment. There is a subtle but important point here. Decoherence explains why quantum alternatives stop interfering and why outcomes become effectively classical. It explains why we can treat the measurement device as having a definite reading for all practical purposes. But decoherence alone does not, by itself, choose which single outcome occurs in a given run. It tells you why the different possible outcomes stop behaving like a coherent blend and start behaving like separate, non-interfering alternatives. In many interpretations, that is enough to account for the classical appearance of the world, because each alternative becomes effectively independent. In other views, an additional story is needed about how one outcome is singled out in our experience. Quantum mechanics, as a predictive framework, remains unshaken either way because it continues to deliver the correct statistics for outcomes. From the standpoint of the viewer trying to build intuition, the most helpful takeaway is simple. Measurement is the process of turning quantum possibility into classical record. The record is not just a symbol on a screen. It is a physical correlation stabilized by amplification and reinforced by the environment. Once a record exists, it becomes meaningful to talk about the outcome as a definite fact, because the fact is now embedded in the world in a way that many other systems can verify. This also clarifies why measurement is not a single, sharply defined moment in time. In some experiments, the boundary between interaction and measurement is gradual. A particle may first become correlated with a microscopic part of a detector. Then that correlation spreads to larger components. Then it triggers an electrical signal, and eventually it becomes a stored bit. The point where you decide a measurement has happened depends on what you count as a record. In practice, physicists set a threshold. When the information has been irreversibly amplified into a macroscopic degree of freedom, And when the outcome can be treated as classical for future predictions, the measurement is complete. This is also why different measurement choices reveal different features of the same quantum system. A measurement is not just reading a value. It is choosing an interaction that couples the system to a particular kind of record. If you couple the system to a device that records one property, you create records about that property, and in doing so, you typically destroy coherence relevant to incompatible properties. This is not merely a statement about your ignorance. It is a statement about what physical records can exist together without contradiction. The structure of quantum theory is tightly linked to the structure of possible measurements, because measurements define which questions the world can answer with stable records. If you keep the focus on records, the phrase collapse becomes less dramatic. Collapse is the shorthand for the fact that once a record exists, you should update your description to match it. In ordinary reasoning, we do this constantly. If you flip a coin under a cup and later lift the cup and see heads, you update your expectations about what you will see if you look again. Quantum measurement is different because the act of obtaining the record is inseparable from the physical process that creates it. But the logic of updating a description after gaining evidence is not foreign. What is foreign is that, before measurement, the theory does not assign definite values to every classical style question, because those definite values would not be consistent with the observed patterns of interference and correlation. This chapter matters for the larger theme of future predicting the past, because it tells you what a measurement really produces. Not a revelation of a hidden story, but a record that makes a story definite. Before the record exists, multiple narratives may be possible descriptions of the process, and the theory only commits to probability assignments for potential outcomes. Once the record exists, the story becomes anchored. That anchoring is physical, not psychological. It comes from amplification, decoherence, and the irreversible spread of information into the environment. Later, when we discuss filtering results and gentle measurements, this will be the ground beneath everything. The difference between a delicate interaction that does not fully create a record and a strong measurement that does. There is, finally, a quiet kind of comfort in understanding measurement this way. It means the universe is not waiting for a mind to notice it. It is continuously making and erasing patterns of information through ordinary physical interaction. Some patterns become stable records, and those records become the facts we share. Others remain fragile, like possibilities that never quite crystallize, and they fade without leaving lasting marks. And when you think about your own day, that same principle can feel oddly gentle. Most of what troubled you today does not need to become a permanent record in your mind. It can be a passing correlation, a momentary signal that does not deserve endless amplification. In the quiet of the night, you can let the unnecessary measurements stop and allow the world to become simple again, one calm outcome at a time. Chapter 4. The trick, keeping only some results. The phrase keeping only some results sounds almost too ordinary to belong in a discussion about quantum mysteries. It sounds like something you do when cleaning a dataset, like throwing out blurry photos or ignoring trials where a sensor malfunctioned. And that is exactly why it is powerful. In quantum physics, this simple act of filtering can create patterns that feel deeply counterintuitive, not because the world is being rewritten, but because conditional statistics can be startling when the underlying process involves quantum uncertainty, interference, and measurement choices that change what information becomes a record. In the most careful language, keeping only some results is called post-selection. You run an experiment many times. You measure something at the end. Then you keep only the runs that match a chosen final outcome and discard the rest. Nothing about the earlier events has been altered. You have not reached back in time. You have simply decided to focus your attention on a subset of trials, a slice of reality that meets a particular condition. Yet when you analyze earlier measurements within that slice, the statistics can look as if the final condition had been influencing the earlier behavior all along. This is not unique to quantum mechanics. In ordinary probability, conditioning can change the meaning of earlier data. If you learn later that a patient tested positive for a disease, earlier symptoms that seemed ambiguous become more diagnostic within that conditioned group. If you discover later that a person was exposed to a particular environment, earlier patterns in their measurements take on a different shape when you analyze only the exposed subgroup. In these situations, nothing mystical has occurred. You are simply describing a population that is no longer the full population. The surprise arises when the subgroup is strongly biased relative to the whole. Quantum post-selection produces stronger surprises for two reasons. First, quantum outcomes are not deterministic in individual runs, so selecting a final outcome is not merely identifying a fixed category that was always destined to happen. It is filtering a distribution. Second, quantum systems can carry correlations that are not easily captured by classical intuition, especially when intermediate interactions are gentle or indirect. These features mean that post-selected subensembles can display behavior that seems to contradict what would be expected from the overall ensemble, even though the overall ensemble remains perfectly consistent with standard quantum predictions. A good way to see the logic without technical detail is to imagine an experiment with an initial preparation and a final measurement. If the final measurement has multiple possible outcomes, the full set of runs is a mixture of all those outcomes. Now imagine that between the start and the end, you also perform some kind of measurement, perhaps one that is subtle, or perhaps one you perform only occasionally. If you analyze that intermediate measurement across all runs, you get one set of statistics. But if you analyze it only within the subset of runs where the final outcome was a particular value, you can get a different set of statistics, sometimes dramatically different. At first, this should not feel illegal. It is the definition of conditional probability. What makes it feel uncanny in quantum physics is that intermediate properties are not always classical facts before they are recorded strongly. An intermediate interaction can imprint partial information, or it can couple to the system in a way that is later sorted into different patterns depending on the final outcome. When you then keep only one final outcome, you are effectively selecting a set of histories that are special. These histories were always present in the full data, but they were diluted by the other histories that you now discard. One of the simplest quantum contexts where post-selection becomes visually striking is in interference experiments. If you have an arrangement where two alternatives can interfere, the overall pattern depends on whether the alternatives remain indistinguishable in the relevant degrees of freedom. Now imagine that the system becomes correlated with an extra feature that can, in principle, mark which alternative was taken. If that marking is present, interference disappears in the overall detection pattern. But if you later measure the marker in a way that does not reveal which alternative it corresponds to, and you then condition on the marker result, interference patterns can reappear within the conditioned subsets. The full data remain non-interfering. The interference emerges only after sorting, because the sorting groups together runs that share a common phase relationship. This is the first deep lesson of post-selection. It can reveal structure that is invisible in the average. The average can look dull because it combines patterns that cancel each other. A post-selected subset can look dramatic because it isolates one of the patterns that was previously hidden by the mixture. This is not unique to quantum physics, but quantum coherence can make the cancellation and reappearance feel especially profound. Another important context for post-selection involves weak or gentle measurements, which we will explore later in detail. For now, the key idea is that a weak measurement does not force a strong, single-run record of the property you are probing. Instead, it produces a tiny shift in a measuring device that by itself is too small to interpret reliably in a single trial. The power comes from repetition. When you repeat the experiment many times, the average shift reveals information about the system. If you then add post-selection, keeping only those runs that end in a chosen final outcome, the average shift for that conditioned group can take values that seem surprising. In some experiments, it can even fall outside the range that one would naively associate with the measured quantity, which is why popular discussions sometimes describe it as impossible values. The correct scientific framing is that these are not direct single-run properties being revealed in a classical way. They are conditioned averages of a particular measurement protocol applied to a post-selected ensemble. They are real in the sense that the meter reading shifts in a reproducible way, and the shift can be predicted by quantum theory. But they do not mean the system literally had an impossible property in the ordinary classical sense. The appearance of impossibility comes from importing classical assumptions about definite intermediate values into a domain where the measurement is purposely designed to be gentle and where the final filtering reshapes the ensemble. The temptation to call this a trick is understandable, but it is important to be precise about what is and is not being done. Post-selection does not create new outcomes. It does not change earlier records. It does not allow you to choose the final outcome on demand in a way that would violate causality. The chosen final outcome occurs only on some fraction of runs, and that fraction can be small. When you post-select, you are accepting that you will discard many trials. The cost of the dramatic pattern is inefficiency. Nature is not granting you a free miracle. It is letting you focus on a rare subset where certain correlations stand out. This inefficiency is not a weakness. In fact, post-selection is a standard and powerful tool in experimental physics. It is used in optics, in atomic physics, and in quantum information experiments precisely because it can isolate the cleanest cases, reject unwanted noise events, and reveal correlations that would otherwise be washed out. When used carefully, it is not a way to fool yourself. It is a way to define a precise conditional question and then answer it with data. The reason post-selection becomes philosophically charged in time-symmetric discussions is that the final condition is imposed after the earlier stages have already occurred. You prepare a system, it evolves, it perhaps undergoes some gentle interactions, and only later do you learn which final outcome occurred. Once you decide to analyze only the runs with a particular final outcome, it can look as though that final condition had been guiding the earlier evolution. But what is really happening is that you are narrowing your attention to a particular class of trajectories within the full set of possible trajectories. A helpful way to phrase the scientific meaning is this: post-selection changes what you are allowed to infer about the past, not what the past physically was. When you condition on the final outcome, you are essentially saying, given that the world ended with this record, what can I say about the distribution of earlier records or meter shifts in the runs that led to it? That is a perfectly legitimate question. It is the same logic that allows you to say, given that a coin landed heads, what is the probability it was flipped in a certain way? In classical settings, such conditioning is usually boring because the underlying dynamics are deterministic, or because the correlations are weak. In quantum settings, the correlations can be sharper, because the measurement choices define which information becomes a record, and because coherence can lead to cancellations and reinforcements that do not resemble classical mixtures. This chapter also helps prevent a common misunderstanding about changing the past. If post-selection were able to influence earlier outcomes in a controllable way, you could communicate backward in time. You could encode a message in a future choice and have that message appear in earlier local data. Quantum physics does not allow this. The dramatic patterns associated with post-selection appear only when you later compare records and sort the data. If you look at the earlier data alone, without knowing which trials will be kept, you do not see the effect. The earlier data remain consistent with the ordinary unsorted statistics. The effect is not a signal that can be extracted in advance. It is a structure that emerges when the full experimental record is considered as a whole. This is why the phrase, keeping only some results, is so central. It explains the apparent backward flavor without invoking exotic mechanisms. The future does not reach into the past as a physical force. Instead, the future supplies information that allows you to carve the past into subsets and notice patterns that were previously hidden. Quantum theory provides the correct rules for predicting those patterns, and experiment confirms them. There is also a deeper scientific elegance here. Post-selection reminds us that physics is not only about what happens, but about what questions are being asked. When you define a question in a conditional way, you are not cheating. You are specifying the context that makes the question meaningful. In quantum mechanics, context matters because measurements are physical interactions that create records. Filtering is a way of defining which records you are including in your description. The strangeness often arises when we forget that we have changed the question by changing the data set we are describing. In the chapters ahead, this will become even more concrete. We will see how post-selection, combined with gentle measurements, can make it feel as though you are learning something about the middle of a process that was never strongly recorded there. But the logic will always return to this point. You are not overriding reality. You are conditioning your description on a final record and then analyzing what patterns appear in the subset of runs that share that record. And if you let the idea echo beyond physics, it carries a quiet existential lesson. Your mind also post-selects. It keeps some moments and discards others, and the story of your day can change depending on which endings you focus on. The universe is not asking you to hold every outcome at once. It is offering you a way to see that meaning can be shaped by what you choose to carry forward, while the world itself remains steady, lawful, and calm. Chapter 5. 2 stories at once. Once you accept the idea from the previous chapter that filtering or post-selection can reshape what patterns you see in the past without rewriting the past, you are ready for the deeper intuition behind this whole topic. 2 stories at once is a plain language way to describe a time-symmetric approach to quantum mechanics, often associated with the two-state vector formalism. The phrase can sound mystical, as if reality is split into competing narratives. In the scientific framing, it is something calmer and more precise. When you know both how a system was prepared and how it was later found, quantum theory lets you describe what happens in between using information from both ends. In ordinary physics, we are used to telling one story that runs forward. You set initial conditions, you apply the laws, and you predict what comes next. That habit is not wrong. It is how most of science works. But it is also a habit built around a practical fact. We typically know the beginning and not the end. We prepare a system deliberately, then we wait to see what it does. The future is unknown, so the natural description flows forward. Quantum physics adds a twist. When you perform a final measurement and then decide to analyze only the runs that ended in a particular outcome, you have effectively specified an end condition for the subset you are studying. The subset is no longer described only by how it started, but also by how it finished. Once you choose to ask questions about what happened in the middle within that subset, it becomes natural to use both constraints. The forward story begins at preparation. The backward story begins at the post-selected outcome. They meet in the middle as 2 pieces of information about one process. It is important to be clear about what this does and does not claim. It does not claim that the future sends a usable signal to the past. It does not claim that you can choose the ending and thereby control earlier events. It is a framework for conditional description, not a mechanism for time travel. The idea is simply that if you are restricting attention to cases with a known final outcome, you can represent that restriction as a kind of boundary condition. The 2 stories are 2 boundary conditions written in the language of quantum states. To appreciate why this helps, consider a familiar difficulty in quantum mechanics. Intermediate questions can be awkward. If you prepare a system and later measure it, you can predict the final outcome distribution easily. But if you ask, what was the system doing in the middle? The answer depends on what you mean by doing. If you mean a strong measurement performed in the middle, you change the system and you create a record, which alters the later statistics. If you mean an unmeasured property, quantum mechanics often refuses to assign a single definite value, because doing so can conflict with interference and other observed effects. So the middle can feel like a fog. Time-symmetric descriptions offer a way to talk about the middle that is disciplined but more informative than a single forward-evolving state alone, especially in post-selected scenarios. The forward-evolving state represents what you can say based on preparation alone. The backward-evolving state represents what you can say based on the final outcome in the subset you kept. Together, They define a more specific description of the intermediate period for that subset, not in the sense of pinning down classical trajectories, but in the sense of assigning consistent conditional probabilities to hypothetical measurements you might have performed in the middle. This is where the language "two stories" becomes useful for a general audience. Imagine you are reading a mystery novel. If you only read the first chapter, you can guess what might happen later, but your guesses are broad. If you only read the last chapter, you can infer what must have been important earlier, but you might misread the clues without the beginning. If you read both the beginning and the end, the middle becomes more constrained. You can interpret details that otherwise looked meaningless. Quantum post-selection is similar, except that the clues are probabilities and correlations, and the interpretation is a precise mathematical framework rather than narrative intuition. Still, we need to keep the analogy from misleading us. In the physical world, the end chapter is not chosen by an author. It is a measurement outcome that occurs randomly according to quantum probabilities. Post-selection simply says you will focus on one of those possible endings and ignore the others. Once you do that, you have more information about the particular run class you are studying. It becomes legitimate to use that information to refine your description of the intermediate stage. A major reason this framework gained attention is that it pairs naturally with gentle measurements. In weak measurement experiments, the goal is to learn something about a system in the middle without forcing it into a single classical outcome at that time. The measurement coupling is designed so that each trial produces only a tiny imprint, not a sharp record. The information appears in averages over many trials. When you add post-selection, the averages can become strongly conditioned, producing patterns that look like they are revealing a hidden intermediate reality. Time-symmetric descriptions provide a clean way to calculate and interpret these conditioned averages. They treat the middle not as a definite classical path, but as a region where two boundary constraints shape the statistics of gentle probes. There is also a philosophical clarity here. Standard quantum mechanics is time-symmetric in much of its underlying evolution. The equations that govern isolated quantum states do not strongly privilege a direction of time. What privileges time in our experience is the growth of irreversible records and the way information spreads into the environment. In the two stories approach, that practical arrow remains real and important, but it is no longer mistaken for a fundamental one-way rule of description. Instead, description becomes flexible, forward only when only the beginning is known, and to-boundary when both beginning and end are specified for the ensemble being analyzed. A common worry is that introducing a backward evolving state sounds like inventing a second physical entity traveling back in time. It is better to treat it as a bookkeeping tool for conditional information. If you already accept the ordinary forward state as a tool for predicting outcome probabilities, then the backward state is the same kind of tool, but conditioned on the final result rather than the initial preparation. It encodes what the final outcome tells you about the system in the interval before it was measured. Nothing supernatural is required. It is the same logic as updating a description once evidence exists, except applied with a time-symmetric mindset. This is also why the two stories language can help prevent overclaiming. The framework is not proposing new experimental predictions that contradict ordinary quantum mechanics. It is a reformulation that aims to make certain conditional questions more transparent. In many cases, the predicted measurable statistics are identical to those obtained using standard approaches. The difference is interpretive and conceptual. It offers a way to talk about intermediate properties, especially in post-selected and weakly probed systems, without pretending that classical definite values existed all along. The scientific debate about this framework often centers on whether it is merely a rephrasing or whether it reveals something deeper about reality. Some physicists value it because it packages conditional reasoning in a particularly elegant way, and because it makes certain results feel less ad hoc. Others argue that standard quantum mechanics already contains the same content, and that adding backward-evolving language risks suggesting retrocausal influence where none exists operationally. Both perspectives can be held in good faith because both agree on the observable predictions. The argument is about the cleanest way to think, not about whether experiments work. What matters for our story is the discipline it offers. When you know the initial preparation and the final outcome for a post-selected subset, you can treat the in-between period as constrained from both ends. The forward constraint tells you what is possible given the start. The backward constraint tells you what is consistent with the end you kept. Together, they shape the conditional probabilities of what a gentle probe might register in the middle. That is two stories at once, not as a mystical claim, but as a careful statement about what information you are using to describe a situation. If you step back, there is something quietly beautiful here. We tend to imagine time as a one-way corridor where causes push forward and the past is sealed behind us. Quantum theory does not break that corridor in the practical sense. Your records remain safe. Your messages cannot travel backward, but it does hint that the way we tell the story of events, especially when records are delicate and filtered, may not be locked to a single direction. The laws can allow a description that uses beginnings and endings as equal pieces of constraint. And that is where a gentle existential reflection can live. Perhaps you do not have to carry your day as a single heavy story that can only be read forward. Perhaps you can let the ending, the quiet of the present moment, soften the meaning of what came before. The universe is still lawful, still consistent, still unimaginably patient. And in that patience there is room for you to rest, even while the deeper rules remain strange and beautiful. Chapter 6. Gentle Measurements. If ordinary measurement is the act of carving a single stable fact into the world, then a gentle measurement is something more delicate. It is a way of asking a question so softly that the system does not have to snap into a sharp recorded answer in that moment. In quantum physics, this matters because strong measurements create durable records. And in doing so, they typically erase the subtle relationships among possibilities that make quantum behavior distinctive. Gentle measurements were developed as a practical technique for learning about quantum systems while minimizing disturbance, and they have also become one of the clearest windows into why quantum description depends so strongly on how information is extracted. The scientific name most often associated with gentle measurement is weak measurement. The word weak does not mean sloppy or low quality. It means the coupling between the system and the measuring device is intentionally made small. Imagine a measurement device as a pointer that can be nudged. In a strong measurement, the pointer is shoved into one of a few distinct positions, leaving a clear macroscopic record. In a weak measurement, the pointer is nudged by only a tiny amount. On a single run, that nudge can be drowned in the pointer's own uncertainty, the unavoidable spread in its initial state. One run does not tell you much. The information appears only statistically. When you repeat the same preparation many times and average the pointer shifts. This is already a familiar idea in science. If you have a very weak signal buried in noise, you can repeat the measurement and average, allowing the signal to accumulate while random fluctuations cancel out. In quantum weak measurement, however, there is an additional subtlety. The noise is not only technical, it is built into the measurement device's initial spread, which must be large if the coupling is weak and the disturbance is to remain small. The cost of gentleness is that each individual measurement result is uncertain. You trade clarity per trial for minimal disruption of the system. Why would you want to do this? Because strong measurements do not merely reveal properties. They help create the very properties they record, in the sense that they force the system into an outcome compatible with the measurement. If you strongly measure which path a particle took in an interference setup, you destroy interference. If you strongly measure a delicate quantum system repeatedly, you can drive it into states correlated with the measurement basis. If you want to understand the system's evolution under conditions where coherence matters, strong measurement can be too invasive. Gentle measurement allows you to gather partial information while leaving the system closer to its undisturbed evolution. A useful way to picture the physical process without relying on formal machinery is to focus on correlation rather than revelation. Any measurement works by correlating the system with a measuring device. In a strong measurement, the correlation is strong enough that the device ends in clearly separated pointer states. In a weak measurement, the device's pointer states corresponding to different system outcomes overlap substantially. Because they overlap, the device reading does not uniquely identify an outcome in a single run. But the overlap also means the system is not forced into one definite outcome as sharply. The joint system-device correlation exists, but it is partial. This partial correlation has two important consequences. The first is that the system is only weakly disturbed. The second is that the information you obtain is not a simple classical attribute like, the system had this value. Instead, the information is encoded in the average behavior of the pointer under repeated trials. What you learn is a statistical feature of the system relative to the measurement you performed, not a deterministic fact about one run. The most famous use of gentle measurements appears when you combine them with the filtering idea from the previous chapter. You prepare the system, you perform a weak measurement in the middle, and you then perform a final measurement. After many trials, you keep only the runs that end in a chosen final outcome and average the middle pointer shifts within that post-selected subset. The resulting average is called a weak value. Weak values can behave in ways that surprise classical intuition. They can be larger than the range you would expect from the usual eigenvalues associated with a strong measurement. They can even appear to take on values that would be forbidden if you treated them as ordinary, pre-existing properties. The scientific point is not that the system secretly possessed an impossible value. The point is that weak values describe conditioned averages produced by a specific experimental protocol, gentle coupling plus post-selection. They are real in the operational sense that they predict meter shifts that experiments observe, but they are not the same as strong measurement outcomes. Confusion arises when a weak value is described as if it were simply the value the system had in the middle. In careful treatments, weak values are understood as contextual quantities that reflect both the preparation and the post-selection, and the particular way the system was weakly coupled to the meter. It may help to slow down and ask what the meter is really doing. In a weak measurement, the meter is designed to respond slightly differently depending on the system's state. But because the response is tiny, the meter cannot be used to reliably separate different outcomes on a single run. Instead, its average shift across many runs becomes meaningful. This means that, at the level of individual trials, the meter reading is compatible with many possibilities, and only in the long-run average do stable patterns appear. When you then post-select, you are not changing earlier readings. You are sorting them into groups and finding that the average shift in a particular group is not the same as the average shift in the whole set. This is an example of conditional statistics made dramatic by quantum coherence and by the fact that the measurement is deliberately non-projective in the ordinary strong sets. Gentle measurements also connect to a broader principle in quantum information. There is a trade-off between information gained and disturbance caused. If you extract a lot of information about a system in one shot, you disturb it strongly. If you disturb it very little, the information gained per trial must be small. This is not a moral rule. It is built into the structure of quantum theory and the way measurement couples systems to meters. It is the same reason why certain properties cannot be simultaneously measured with arbitrary precision using strong measurements, and why attempts to do so lead to back action that changes the system. In practice, weak measurement techniques have become valuable tools. They can be used to estimate small effects, amplify certain signals in a controlled way, and probe systems without fully collapsing them in the strong measurement sense. They have been applied in precision metrology, in studies of foundational questions, and in experiments that explore quantum trajectories, where one tries to reconstruct a likely path of a system's state over time, conditioned on a measurement record. In these modern contexts, trajectory does not mean a classical path through space. It means an evolving state estimate conditioned on continuous, partial measurement results. The measurement is gentle enough that it does not abruptly force the system into a single eigenstate, but it is informative enough when accumulated over time to update the estimate. This brings us to an important conceptual point that avoids repeating earlier chapters too directly. Measurement is not just an endpoint, it can be a continuous process. In many experiments, information is extracted gradually, and the system's state changes gradually in response to the measurement's back action. The theory describing this involves stochastic elements, because the measurement outcomes are fundamentally probabilistic. But the evolution is not random in an uncontrolled way. It is random within a structured framework, where the conditional state changes reflect the balance between the system's natural dynamics and the information being gathered. Gentle measurements are one of the main settings where this gradual picture becomes intuitive, because you can literally watch the estimate of the system's state drift as new bits of partial information arrive. In the context of our overall story, gentle measurements are the bridge between the future changes the past as a headline and conditional inference as the sober scientific truth. When you measure gently in the middle and then filter on a final outcome, the middle information you gather appears to be shaped by the final constraint. That is not because the future reached back and pushed the meter. It is because the meter readings are weak, ambiguous per trial, and therefore highly sensitive to how you later sort the data. When you keep only one ending, you keep a set of trials whose subtle correlations align in a particular way, and the average pointer shift reflects that alignment. There is also a lesson about language. Words like peak, probe, and measure suggest a single act of revealing what is there. Weak measurement forces us to adopt a different vocabulary. It is less like reading a number off a dial and more like nudging a system and watching how the statistical response accumulates. It is a method for learning within the limits of quantum information, not a loophole around those limits. And yet, the result can still feel like a whisper from the system's interior. A gentle measurement can reveal patterns that would vanish under strong measurement, and in that sense, it gives you access to a subtler layer of quantum behavior. It reminds you that the world does not always offer sharp answers on demand. Sometimes the most truthful answers appear only when you ask softly, repeatedly, and with patience. That patience has an existential echo if you let it. You do not need to force clarity out of everything at once. Some truths in life, like some truths in quantum physics, become visible only in gentle averages over time. Tonight, you can allow the day's noise to settle and let only the simplest, most stable patterns remain. The universe can be strange without being hostile, and your mind can rest inside that strangeness as if it were a quiet, distant sea. Chapter 7. The famous example, delayed choice. Among all the ideas that make quantum physics feel like it is bending time, delayed choice experiments have a special reputation. They are often described with dramatic language, as if a decision made later forces a particle to decide what it was earlier. That description is emotionally compelling, but it is not the most accurate way to think. The scientific heart of delayed choice is quieter and more precise. Quantum predictions depend on the entire measurement context, and if the context is chosen late, the late choice determines which kind of description fits the data. The past is not rewritten. Rather, the type of past story you are allowed to tell depends on whether a stable record exists that distinguishes alternatives. The classic intuition begins with a simple interference setup, where a quantum system has two alternative ways to reach a detector. If the experiment preserves indistinguishability between the alternatives, the detection statistics show interference. If the experiment creates which alternative information, interference disappears. This is one of the most well-tested patterns in quantum physics. It is not merely a matter of human knowledge. It is a matter of physical information. If the world contains a reliable record that can, even in principle, distinguish the alternatives, then the interference terms do not appear in the observed statistics. Delayed choice takes this familiar relationship and rearranges the timing. The apparatus is designed so that the quantum system has already passed the region where the two alternatives diverge before the experimenter chooses whether to combine the alternatives in a way that allows interference or to separate them in a way that reveals which alternative was taken. In the naive classical picture, the system should already have chosen a route earlier. So if a late decision changes whether interference is observed, the mind wants to say, the late choice must have changed what the system did earlier. But quantum mechanics does not require us to assign an early, definite route in the absence of a record. Instead, it tells us to compute probabilities for the outcomes that will be recorded at the end given the full measurement arrangement. If the arrangement, including the late choice, is such that no which alternative information is recorded, then the quantum state evolves in a way that preserves coherence between the alternatives, and interference can appear in the final detection statistics. If the arrangement is such that which alternative information is recorded, coherence is effectively lost and interference does not appear. The timing of the choice does not change the rule. It only highlights that the rule refers to physical records and measurement context, not to a hidden classical history. To make this concrete without technical details, it helps to focus on what the final detectors are actually sensitive to. In an interference setup, detectors that register interference are detecting a combined effect of both alternatives. They are sensitive to relative phase, which is the feature that allows possibilities to reinforce or cancel in the probability distribution. Detectors that register which alternative information, by contrast, are arranged so that a detection event can be associated with one alternative rather than the other. That arrangement turns the alternatives into distinct records. Once they are recorded distinctly, interference is absent because the pattern is no longer shaped by a coherent combination. It is shaped by a mixture of distinguishable contributions. In delayed choice, you are not changing the system's earlier journey by willpower. You are choosing what kind of record the experimental setup will produce. That is why the results are consistent with causality in the practical sense. If you look only at the early part of the experiment, before the late choice is implemented, there is no local signature that reveals what the choice will be. The system's behavior is not carrying a readable message into the past. The distinctions appear only in the final recorded pattern, which depends on the final measurement context. A key historical motivation for delayed choice thinking was to challenge a certain form of naive realism. The idea that a quantum object must always have traveled as either a wave or a particle in a classical sense, independent of how it is measured. Delayed choice shows that insisting on such a classical story can lead to confusion. If you choose an interference measurement, the data support a wave-like description in the sense of interference patterns. If you choose a which alternative measurement, the data support a particle-like description in the sense of localized detections associated with a path. Delayed choice emphasizes that these descriptions are not simultaneous features of a single classical trajectory. They are context-dependent ways of summarizing what the experiment records. It is also worth noticing something that is often lost in popular accounts. Even when interference is observed, the detections are still discrete. You get localized clicks or spots. Interference shows up only in the distribution of many events. So the wave-like aspect is not a literal smear of a single particle in a single run in the way a classical wave spreads continuously. It is a wave-like rule for probabilities. Conversely, even when which alternative information is available, quantum probabilities remain. The system does not become a perfectly deterministic classical particle. It becomes a system whose outcomes follow non-interfering statistics consistent with distinguishable alternatives. Delayed choice, therefore, is not about toggling between fully classical modes. It is about how probability structure changes when coherence is preserved or destroyed by the measurement context. The most dramatic modern variants of delayed choice connect this idea to entanglement and to what is sometimes called a quantum eraser. In those experiments, which alternative information may be stored in an entangled partner system rather than directly in a path detector. If the partner system carries information that could, in principle, reveal the path, then interference disappears in the straightforward detection statistics. But if the partner system is later measured in a way that does not reveal the path, and instead sorts the data into groups that share a coherent relationship, interference can reappear within those sorted groups. The timing can be arranged so that the partner measurement happens after the original detection event, which tempts people again into retrocausal language. The scientific interpretation remains the same. The overall detection pattern does not suddenly become an interference pattern by a late decision. The interference appears only in correlations revealed after sorting the data based on the later measurement outcomes. This protects causality. No one at the earlier detector can look at their local data and learn what choice will be made later. The effect is not a backward signal. It is a property of joint statistics across correlated records, made visible only when the full dataset is analyzed together. This brings us to the simplest and most important point delayed choice teaches. In quantum physics, a which path fact is not a free gift. It must be purchased with a record. If you design the experiment so that the alternatives remain indistinguishable in the relevant degrees of freedom, the theory does not compel you to say that one path was taken as a hidden fact. If you design the experiment so that the alternatives are distinguishable and that distinction is recorded, then a path description becomes meaningful. Delayed choice is unsettling only if you assume the path fact must exist regardless of whether it is recorded. Quantum mechanics suggests that, at least for the kinds of experiments where interference is observed, that assumption is not necessary and can be misleading. Delayed choice also helps clarify the phrase, "The future changes the past," in a mature way. What changes is not the physical past, but the consistency of different descriptions. If the late measurement context makes interference relevant, then the correct description of the intermediate stage is one that keeps coherence between alternatives. If the late context makes which alternative information relevant, then the correct description is one where coherence is effectively absent in the relevant basis. Both descriptions can predict the correct final records in their respective contexts. The late choice selects which description is appropriate because it selects which records exist in the completed experiment. There's an even calmer way to say this. A physical process is not obligated to carry a single classical narrative if no record exists to support that narrative. Quantum theory gives you a set of rules for predicting what will be recorded, and those rules can be time-symmetric in their underlying structure. Delayed choice highlights that our ordinary storytelling habits can be too eager to assign definite histories where the experiment does not support them. When the experiment is designed so that the history is not recorded, the correct approach is to speak in terms of probabilities and coherence, not in terms of a definite earlier path. For the listener, the value of delayed choice is not only that it is famous, it is that it teaches intellectual humility in a concrete, testable way. It shows that the universe does not always answer the question you thought you asked. It answers the question your apparatus actually encoded. The measurement context is not a superficial detail. It is part of the physical situation. And the timing of that context can be surprisingly flexible without changing the meaning of the results. Because what matters is the complete set of records produced by the full experiment. In the quietest sense, delayed choice can also be oddly reassuring. It suggests that reality is not a fragile story that can be damaged by curiosity. It is a stable structure of lawful predictions, and those predictions remain consistent even when our intuition protests. The world does not break when you question it. It simply asks you to be precise about what you mean and to let the evidence define the story. And if your day has felt like a tangle of competing narratives, you can let it soften here. You do not have to decide everything tonight. You can let the future bring its own clarity in time and allow your mind to rest in the present, where the simplest record is your breath, quietly continuing. Chapter 8. What it cannot do. Once you hear phrases like, "the future predicts the past," it is natural for the imagination to run ahead of the science. If a later choice seems to reshape how we describe an earlier moment, then why not use that to do something dramatic? Why not send a warning to yesterday, undo a mistake, or communicate information backward through time? This is exactly the point where careful physics matters most. Quantum mechanics can produce correlations that look retroactive when you filter data or compare records later. But it does not permit controllable influence that rewrites earlier outcomes. The difference between those two ideas is not a minor technicality. It is the boundary between subtle statistics and broken causality. The most basic limitation can be stated plainly. You cannot use post-selection, delayed choice setups, or gentle measurements to change an earlier record that already exists. If a detector has clicked and that click has been amplified into a stable macroscopic record, nothing you do later can make the click unhappen. You can choose how to sort your data set, you can choose which subset to analyze, and you can choose which interpretation you prefer, but the recorded facts remain. This is not an extra rule added to save common sense. It is built into how measurements work physically. Records are not airy labels. They are correlations distributed into many degrees of freedom in detectors, electronics, memory, and environment. Changing them would require reversing a vast number of microscopic interactions, which is not achievable in ordinary conditions. And more importantly, quantum theory itself does not provide a mechanism for later choices to deterministically overwrite earlier macroscopic outcomes. A second limitation is more subtle and more central to the future predicting the past theme. Even when later choices affect which patterns appear after conditioning, they cannot be used to transmit a usable signal to the past. The reason is that the dramatic effects show up only when information from different parts of the experiment is brought together and compared. If you isolate the early time data before the late time choice is known, that early data alone does not reveal what choice will be made later. In other words, the early time outcomes have statistics that, by themselves, remain consistent regardless of later settings. Any difference appears only in joint correlations that require combining records that are not locally available at the earlier time. This is closely related to what physicists call no signaling. In quantum theory, entanglement, and other non-classical correlations can link outcomes in striking ways, but they do not allow faster-than-light communication or backward-in-time messaging. If they did, relativity and causality would be in immediate trouble, because different observers would disagree about the time order of space-like separated events. Quantum mechanics has been constructed and experimentally confirmed in a way that preserves this operational causality. Correlations can be strong, but controllable signaling through those correlations is forbidden. A helpful way to feel this limitation is to recall what post-selection actually costs. Post-selection is not a magical power to choose outcomes. It is the act of discarding runs that do not match a chosen final condition. If the chosen condition is rare, you discard many runs. That means you cannot guarantee success on demand. And because you cannot guarantee the chosen outcome, you cannot encode a message reliably. Imagine trying to communicate backward by deciding, in the future, whether to post-select on one final outcome or another. The person in the past would need to see a difference in their local data before the future choice is revealed. But they do not. The difference only appears when the past data are sorted by the future outcome, and that sorting requires knowledge that arrives later. Without that later information, the past data remain an ordinary mixture. Delayed choice experiments show the same constraint in a different disguise. When you choose late, whether to preserve interference or to extract which path information, the final pattern changes accordingly. But no observer looking only at an earlier stage can tell what you will choose. There is no marker that travels backward. The system does not carry a readable note from your future decision into the earlier region. What changes is which measurement context completes the experiment, and therefore which kind of final record is produced. The experiment is not completed until the detection context is fixed. Quantum mechanics predicts the results of the completed experiment, not an independent classical history that must exist in advance. Gentle measurements add another source of confusion because weak values can look outrageous in popular retellings. If a conditioned average seems to take an impossible value, it can sound as if the system had a forbidden property and that the future selection forced it. But weak values are not ordinary strong measurement outcomes. They are protocol-dependent averages obtained under gentle coupling and post-selection. They cannot be used to read off a hidden number from a single system on demand. They do not let you extract unlimited information without disturbance. They do not allow you to evade uncertainty by clever filtering. They are consistent with quantum information trade-offs. The very gentleness that preserves coherence makes individual trials ambiguous, and the post-selection that creates a striking conditioned average discards the majority of runs. There is also a more general limitation that is easy to state but easy to underestimate. In quantum mechanics, you cannot freely assign definite values to all properties at all times in a way that reproduces the theory's predictions for every possible measurement context. This is not just about uncertainty in the everyday sense. It is about the structure of the theory itself and the way measurement choices define what properties can be treated as definite. Time-symmetric descriptions and post-selection do not restore a classical picture where every question always had a single hidden answer. They refine conditional inference within quantum rules. They do not revive the classical dream of a complete, measurement-independent catalog of facts. Another boundary is practical and physical rather than philosophical. Any attempt to scale these effects into the macroscopic world runs into decoherence. The retro-looking correlations rely on maintaining coherence or carefully controlling which information becomes a record until the end. Macroscopic objects are constantly interacting with their environments. They radiate heat, scatter light, vibrate, and exchange information with countless degrees of freedom. That information acts like uncontrolled measurement. It creates records. Once records are widespread, interference between macroscopically distinct alternatives becomes effectively impossible to observe. This is why you do not see cats in coherent superpositions of clearly different classical states in daily life, and it is why you cannot use quantum post-selection tricks to rewrite everyday history. The environment locks things in long before you could arrange delicate filtering. It is worth noting that none of these limitations make the phenomena less real. They simply locate what kind of reality is on display. The reality is in correlations, in conditional patterns, and in lawful statistics. The reality is not in a loophole that lets you bend causality at will. Physics is full of effects that are subtle but strict. Quantum mechanics is one of the strictest. It gives astonishing possibilities for computation, sensing, and secure communication, but those possibilities coexist with hard constraints that prevent paradox. The same formalism that allows non-classical correlations also blocks them from becoming causal weapons. So when we say in a soft and careful way that the future can predict the past, we mean something modest and precise. We mean that if you condition on a final outcome, you can infer patterns about earlier gentle probes within that conditioned subset. You can use both ends of an experiment to refine what you say about the middle. You can find that certain descriptions of the past are inconsistent with the full set of records, while others fit beautifully. But you cannot send a message to the past. You cannot change a recorded outcome. You cannot create contradictions that allow you to win a game against time. The clearest way to keep your intuition aligned is to remember what information is available and when. If an effect appears only after data are grouped using knowledge that arrives later, then the effect cannot be used as a signal earlier. If an effect depends on discarding a large portion of trials, then it cannot be used as a reliable tool for controlling outcomes. If an effect depends on preserving coherence, then it will vanish when uncontrolled environmental records form. These are not loopholes. They are the guardrails that keep quantum weirdness consistent with a universe where cause and effect remain meaningful. There's a quiet existential comfort in guardrails. The world can be strange and still be safe. The universe can allow deep uncertainty in single events while still protecting the consistency of time, memory, and record. Your life is not balanced on the edge of a fragile paradox. It is held inside a set of rules that have survived every experimental challenge we have thrown at them. And perhaps that is enough for tonight. Even if the future cannot reach back and repair the past, it can still reshape what the past means to you, gently and honestly, as you learn and rest. You are allowed to let today settle into its final form without fighting it, and to feel for a moment the steady calm of a universe that does not break when you stop holding everything so tightly. Chapter 9. Why scientists still argue about it. By this point in the story, the experimental facts are not the main source of uncertainty. The ability to predict quantum statistics, to build reliable devices and to test subtle correlations is one of the great achievements of modern science. The argument is not about whether quantum mechanics works. It works extraordinarily well. The argument is about what kind of picture, if any, should sit underneath the predictions. When people say scientists still argue about quantum ideas that seem to involve the future shaping the past, they are usually talking about the interpretation of the formalism, not the formalism's accuracy. The experiments are consistent. The meanings we attach to them are where the debate lives. One reason this debate persists is that quantum mechanics is, at its core, a theory of probabilities linked to measurement outcomes. It tells you what you should expect to be recorded given a preparation and a measurement context. It is less explicit about what is happening between preparation and measurement if no strong record is made in the middle. That gap invites multiple ways of thinking. Some approaches treat the quantum state as a physical entity that evolves. Some treat it as a tool for organizing expectations. Some treat it as incomplete, with hidden variables below. Others treat it as complete, with many branches or many consistent perspectives. Time-symmetric descriptions, including the idea of using both a beginning condition and a filtered ending condition, add a particularly sharp test for these philosophical instincts. They make it hard to pretend that a single, classical-style story is always sitting behind the statistics. To understand the disagreement, it helps to notice the difference between two kinds of questions. One kind is operational. What will the detectors do? What patterns will appear? What correlations will be observed? Quantum mechanics answers these with ruthless success. The other kind is ontological. What is real in the theory? What exists when no one is looking? What does a quantum state represent? These questions are not directly resolved by the success of the predictions, because multiple interpretations can produce the same observable statistics. Scientists are trained to prefer questions that can be settled by experiment. So there is a natural tension when a debate seems to live partly outside direct empirical resolution. Time-symmetric approaches make this tension more visible. When you use post-selection and gentle measurements, it can look as though you are learning something about the middle of a process that depends on how the process ends. One group of physicists sees this as a clean way of doing conditional inference. Given both preparation and final selection, the best description of intermediate statistics uses both constraints. Another group hears two constraints and worries it invites language that sounds like retrocausality, as if the future were sending influence backward. Even if no usable backward signal exists, the very framing can feel like a metaphysical commitment. That is where argument begins. A major source of disagreement is what people think the quantum state is. If you treat the quantum state as something physically real, like a field-like entity describing the system, then introducing a backward evolving state can sound like doubling reality. It can feel as if you are proposing two physical waves, one moving forward and one moving backward, meeting in the middle. Some physicists find that elegant. Others find it unnecessary or confusing, especially if the same measurable predictions can be obtained using standard forward-evolving descriptions and ordinary conditional probability. If you treat the quantum state as information rather than matter, the picture changes. On that view, a backward evolving state is not a second physical wave. It is simply a way of encoding information about the system conditioned on the final outcome. The debate then becomes partly semantic. Is the time-symmetric language genuinely clarifying, or is it packaging ordinary conditioning in an evocative story that risks misunderstanding? This is why the argument often sounds like two people talking past each other. They are not always disagreeing about calculations. They are disagreeing about what the calculations should be taken to mean. Another reason scientists argue is that quantum mechanics sits at the intersection of two powerful principles that are not easily reconciled in everyday intuition. One is the time symmetry of many fundamental microscopic laws. The other is the apparent one-way flow of events in our experience, tied to entropy and the growth of records. Time-symmetric quantum formalisms take the first principle seriously and attempt to express quantum description in a way that does not privilege the past to future direction as the only legitimate viewpoint. Critics respond that the second principle is not just psychological. The macroscopic arrow of time is physically grounded in thermodynamics and in the irreversible spread of information. So they worry that time-symmetric language can obscure the practical fact that measurements create records in a one-way, irreversible manner. Both sides can be right in different senses. At the microscopic level, the mathematical machinery can be written in a time-symmetric way, and conditional descriptions with both boundary conditions can be natural. At the macroscopic level, the world we inhabit is dominated by irreversible record creation, so descriptions that ignore that can mislead. The argument is partly about which level of description is most appropriate for talking to humans who live in the macroscopic world. There is also a methodological tension. Some scientists prefer interpretations that add as little as possible beyond the successful predictive rules. If a time-symmetric formalism reproduces standard predictions, they may see it as optional, a matter of taste. Other scientists value interpretations that provide a more unified conceptual picture, especially if it reduces the sense of arbitrary collapse or clarifies why certain conditional results look surprising. For them, time-symmetric approaches can feel like progress even if they do not yet produce new experimentally distinguishable predictions. The argument then becomes about what counts as progress: only new predictions, or also clearer understanding. Weak measurement and post-selection intensify this because they generate results that can be described in multiple ways. One description emphasizes conditioned averages and careful statistics. Another emphasizes intermediate values that seem to exist between measurements. Depending on which language you choose, the same experimental result can sound either like a sober statistical fact or like a radical claim about hidden intermediate reality. Scientists argue because language matters. The danger of misleading language is real, especially in a field where intuition is fragile. But so is the danger of overly cautious language that hides genuine conceptual lessons. A further source of argument is that quantum foundations is a place where the boundary between physics and philosophy becomes unusually thin. In many areas of physics, you can proceed without worrying about interpretation because the models map to tangible mechanisms. In quantum mechanics, you can build lasers, semiconductors, and quantum sensors while remaining agnostic about what the wave function really is. That pragmatic success can reduce pressure to settle interpretive questions. Yet interpretive questions keep returning because they shape what kinds of new theories scientists search for and what they consider plausible as deeper explanations. If you believe the quantum state is complete, you might lean toward branching or relational pictures. If you believe it is incomplete, you might search for hidden variable theories. If you believe time symmetry is fundamental, you might explore retrocausal or two-boundary ideas more seriously. There are also genuine technical subtleties that keep the debate alive. When you describe quantum measurement as state update, is that update a physical process or a change in knowledge? If it is physical, when and how does it occur, and what selects a single outcome? If it is knowledge, knowledge of what, and is the quantum state merely an agent's bookkeeping? If decoherence explains why interference disappears between macroscopic alternatives, does it also explain why only one outcome is experienced? Or does it leave a gap? These questions do not vanish simply because we can compute probabilities. They remain because our explanatory standards in science usually include not only prediction, but also mechanism. Time-symmetric descriptions offer one response to this discomfort. They suggest that part of what we call collapse might be better understood as conditioning on boundary information. The preparation sets one boundary, the final outcome sets another, and the middle description is a bridge between them. This can make the abruptness of collapse feel less fundamental. But critics point out that conditioning on a final outcome is itself a special act, and in the real world, we do not generally know final outcomes in advance. Post-selection is a laboratory procedure, not a universal law. So they argue that time-symmetric language is a useful tool for certain experimental analyses, but not necessarily a fundamental account of measurement. This is why the argument persists. It is not a disagreement between people who accept quantum experiments and people who deny them. It is a disagreement about explanatory taste, about what it means for a theory to describe reality, about whether the quantum state is substance or information, and about how much conceptual structure we should add beyond the minimal predictive core. In many ways, it is a sign of health rather than failure. The field is honest about the difference between we can calculate it and we understand it. When a theory is as successful as quantum mechanics, the remaining debates are inevitably about the deepest layers. And in the quietest sense, this ongoing argument can be comforting. It means the universe is still large enough to leave room for wonder, even after we have measured so much. The foundations are not a crack in the world. They are a reminder that knowledge is a living process, and that even the most precise science can contain open questions about meaning. You can let that be gentle tonight. You do not need to resolve every debate in your own mind. It is enough to know that the world remains consistent and that your small awareness is allowed to rest inside a reality that is both reliable and still mysterious. Chapter 10. The simple takeaway. After all the strange phrases, all the careful limits, and all the subtle experiments, the simplest takeaway can sound almost disappointingly ordinary. Yet it is exactly the kind of ordinary truth that becomes powerful once you feel it clearly. Quantum mechanics does not say the future can reach back and rewrite history. It says something both gentler and more precise. What you are justified in saying about the past depends on what information the world ends up recording and on how you choose to condition your description on those records. The past, in quantum physics, is not always a single hidden storyline waiting to be uncovered. It is a structure of probabilities that becomes a definite narrative only when records make it definite. This is easiest to understand if you separate three things that we often blend together in daily thought. One is the physical process itself. Another is the evidence the process leaves behind. The third is the story we build from that evidence. In everyday life, these merge because the world is constantly producing abundant, redundant records. Light scatters from objects, sound waves spread, heat dissipates, and countless microscopic interactions copy information into the environment. Because the evidence is so widespread, the story becomes stable. There's little room for ambiguity, and the notion of a single definite past feels obvious. Quantum experiments that inspire future predicts the past headlines are the opposite. They are designed to keep evidence from becoming redundant too early. They carefully prevent the environment from making strong records of certain distinctions, such as which of two alternatives occurred. When those distinctions remain unrecorded, the theory does not need to assign them as definite facts. Instead, it assigns a coherent probability structure that can produce interference and other non-classical effects. Only when a measurement is performed that creates a durable record do those distinctions become definite in the classical sense. From that viewpoint, the delayed choice family of ideas becomes less dramatic. A late choice does not change an earlier physical event. It changes which measurement context completes the experiment, and therefore which records exist in the finished dataset. If the completed arrangement preserves coherence between alternatives, interference can appear in the final detection statistics. If the completed arrangement records which alternative occurred, interference is absent. The late timing is startling only if you assume the system had to commit to a classical narrative before the final record existed. Quantum mechanics suggests that commitment is not required, and in many cases, not even a coherent demand. Post-selection makes the same lesson clearer, because it reveals how strongly conditional description can reshape the patterns you see. When you run an experiment many times and then keep only the trials that end in a chosen final outcome, you are not editing earlier events. You are selecting a subset. Within that subset, earlier statistics can differ from the overall statistics, sometimes dramatically. This is conditional probability brought into a domain where quantum coherence and measurement context can make conditional patterns look uncanny. The future, in this sense, predicts the past because the final record provides information that lets you refine your inferences about what likely happened in the middle for the trials that share that final record. Gentle measurements fit neatly into the takeaway as well. A weak measurement does not force a strong record in the middle. It creates a tiny, ambiguous imprint. One run reveals almost nothing. Over many runs, averages reveal consistent patterns. If you then combine gentle probing with post-selection, the conditioned averages can look surprising, even impossible to a classical mind. The correct interpretation is not that the system had forbidden properties. The correct interpretation is that you are observing a specific measurement protocol's conditioned statistical signature. The protocol is real, the meter shifts are real, the results are reproducible and predicted by quantum theory, but they do not grant you the ability to reach backward and rewrite a settled past. In other words, the simple takeaway is that quantum mechanics is a theory about what can be known through physical records and how those records arise. It does not treat all questions as if they must have pre-existing answers independent of measurement. It treats measurement as a physical process that creates correlations and stabilizes them into records, often through amplification and the rapid spread of information into the environment. When records exist, the past is firm. When records are deliberately prevented from forming, the past is not a single classical narrative in the way we are used to. This framing also explains why causality survives intact. If later choices truly changed earlier recorded outcomes, you could send messages to the past. Quantum mechanics does not allow that. Any retro-looking effect appears in correlations that become visible only when the full set of records is brought together and analyzed. Local data at an earlier time do not carry a readable signature of later choices. That is not an accidental loophole. It is an essential structural feature that keeps quantum non-classicality consistent with the broader causal structure of physics. The world may allow surprising correlations, but it refuses paradox. At this point, a listener might reasonably ask, so what is actually real? The most honest scientific answer is that quantum theory gives a reliable map from preparations to measurement outcomes, and different interpretations offer different pictures of what that map means. Some treat the quantum state as a physical object, some treat it as information, some treat outcomes as branching, some treat properties as relational, some treat collapse as fundamental, others as emergent. The simple takeaway of this video does not depend on choosing one interpretation. Across interpretations, the practical message remains the same. When you condition on later information, you can legitimately change what you infer about earlier stages, but you are not changing earlier stages themselves. This might sound like a small point, but it is a deep one. It is the difference between a universe that is logically stable and a universe that is vulnerable to contradiction. Quantum physics, despite its reputation, belongs firmly to the stable category. It is weird in its rules for probabilities and records, not chaotic in its logic. The mathematical structure is consistent. The empirical record is consistent. The weirdness is our expectation that the world must always supply a single classical story, even when we have deliberately designed an experiment to avoid creating the records that would support such a story. The calmest way to carry this forward is to treat the phrase, "the future predicts the past," as a shortcut for conditional description. If you know how a system began and how it ended, you can describe the in-between in a way that uses both constraints. This can make the intermediate behavior look like it was shaped by the ending, but it is shaped by the information you are conditioning on, not by a physical signal traveling backward through time. The future does not reach back like a hand, it clarifies like a lens. There is also a broader scientific lesson in that. Many of the most reliable statements in physics are not statements about what must be there in a naive sense. They are statements about what can be inferred, what can be measured, and what patterns must appear when you repeat an experiment. Quantum mechanics is not less real because it speaks this way. It is more careful. It refuses to pretend knowledge exists where records do not. That refusal can feel like a loss at first, but it is also a kind of intellectual honesty that gives the theory its power. And if you let yourself step back from the technical details, there is a human echo. Much of what makes a day feel heavy is not the day itself, but the story we keep replaying from the evidence we choose to hold. Quantum physics is not telling you to deny facts. It is telling you that facts are anchored by records, and that meaning is often anchored by what you choose to condition on. You cannot rewrite what happened, but you can change which parts of it you amplify into your attention, and which parts you let dissolve into the background noise of time. In the end, the simple takeaway is that reality at small scales is not a single line. It is a web of lawful possibilities that becomes a single line only when the world makes it so through records. The future does not invade the past, but the full set of information available at the end can reshape the best description of what the past was like for the runs you are studying. That is not magic. It is conditional reasoning carried out in a universe where measurement is a physical act that creates facts. And tonight, that can be a gentle thought rather than a dizzying one. The universe can hold uncertainty without losing coherence, and you can do the same. You can let the unanswered questions stay unanswered for now and still feel safe inside the steadiness of the laws that guide everything. For a little while, you can simply be here, breathing, while the cosmos continues its quiet, patient consistency around you. And that's the quiet truth. Quantum mechanics doesn't rewrite history. It changes what patterns you can infer when you only keep certain results, and when you choose what counts as a record. The universe stays consistent, even when our intuition feels it wobble. If you're still awake, I've got another calm science video waiting for you, something gentle to keep your mind drifting. And if you're already fading out, that's perfect too. Sweet dreams, my friend, and may you sleep peacefully among the stars.